that too.
It
sounded long to me.
Then why are you leaving it out there? One of the back tables.
What?
So let me start by first saying a couple things about the end of the semester. We have, so what's left? Our exam 4, our last exam, is a week from Friday, so that's Friday, May 6th. And we have a final lab exam. I didn't look up when. I think that's probably the Thursday before. And the AP test is Monday, May 9th. And then this isn't on the syllabus, but this is something I talked to Meredith about this, and I'm going to offer this option, a makeup exam. It's just basically going to be a new version of exam 4. I mean, it's going to be a cumulative exam. But that score can replace any one of your first 4 exams. So if you're not happy with any one of your first 4 exams, you can do the makeup on, this is, I think Meredith and I agreed, Tuesday morning at, I don't remember. I should have looked at all this stuff before I started writing it, but I think it's at the normal time. Yep.
May 5th is the calculus BC test in the morning.
Oh, so you're not going to be here?
Right.
Okay. Okay. Well, I guess maybe we'll do that on Tuesday of next week.
What?
The lab exam.
Oh, the lab exam. Okay. Well.
Yep.
Is the makeup exam going to be on May 10th?
May 10th. Yes. So that's the stuff that's coming up. And this stuff really has all has one thing in common. Okay? What you need to do between now and this stuff, well, the lab exam is kind of its own thing, but definitely the other 3, is you need to between now and then, you need to skim all the notes. Your goal is to remember everything I said. That's maybe not some of the stupid stuff about the bell signifying God bless you and stuff, but all the stuff that I said relating to physics. Your goal is to remember all that stuff. I know that's a lofty goal or whatever, but that's what you should be. That's your goal. And then the second thing is you should look. Let me say this a little stronger. You should know how to do all the assignment problems. And the best way, I think, to do that is, so you need to start looking back at this stuff now, okay? Because you don't have a lot of time to do this. I would say skim the notes and look back at the problem, starting at the beginning. And just ask yourself, do I know how to do this problem? Do I know the steps? What are the steps? And if you know, you're like, yes, I know how to do this, then move on to the next one. If you get to one that you don't know how to do, think about where you're unclear on what to do, and then look at the solution. Okay? If you're more unclear than that, then you have to work through the problem. Okay? So that's your goal. If you get to the point where you remember everything I said and you know how to do every problem I have assigned, you're going to get 100 on exam 4 and the makeup test, and you're going to do great on the AP test. Okay? So that's kind of the upper level of what you're trying to get to. Okay? Anybody have any questions about? Yep.
Could the makeup exam technically, could you use it to replace a homework quiz score? It's like unbelievably bad.
Well,
What's the point of that actually being more valuable to you?
that is a funny question. Yes, that is fine with me. But I think if that's your position, then you don't have much to worry about. You know what I mean? But yes,
Do that, so.
yes.
Okay.
Because I think each homework quiz is only worth about 2% of your grade or something, right? Maybe a little more, but less than 5. Any other questions? Okay, so here is what we've been talking about. We're on our way to the rotational version of Newton's second law. And we just started talking about the moment of a force about an axis. And there are two definitions. The first one was that the absolute value of the moment about the axis is equal to the force times the distance, where positive is counterclockwise and negative is clockwise. The second definition we haven't gotten to yet, but I'll just write it out. That uses a calculation called the cross product. So MA is equal to a row vector crossed with a force vector, and that does the signs for you. The units of moment are force times length. And so in SI units, that's Newton meters. Okay, so we're done with this one. And you kind of need to be able to use both of these two definitions, because sometimes one is a lot easier and sometimes the other one is a lot easier to use. So you could just say, like, I'm only going to remember one and always do it that way, and wouldn't be the end of the world, but you'd be adding a lot of extra effort. Okay, so this is called, this operator is called the cross product. Have any of you seen cross product in a math class? Okay. Anyone else? Yeah. Okay. Well, it's easy to calculate. The cross product of the vector AB and the vector CD is equal to, so the cross comes from the fact that you're multiplying these two, AD, and then you're multiplying these two and subtracting that. So it's AD minus BC. That's the cross, going across. It's really a three-dimensional thing. You can think of this as a scalar. But really, it's a vector pointing in the z direction. And if you're dealing with fully three-dimensional vectors, it gets a little more complicated, but it's the same idea. This is all we're going to use. So the thing to notice for us, since moment is a cross product, so since MA is a cross product, it's really a vector in the z direction. We're not going to use that fact, or that's not going to really come into things, but in your next physics classes, or if you take engineering classes, you're going to use that fact. TI calculators. They'll do the cross product for you. You just have to enter in the function, I think it's lowercase CROSS uppercase P, and then you have to enter in the two vectors, and it'll calculate that for you. So it's sort of nice when you get used to it. If you need help figuring that out, let me know. Okay, so definition 2. Of rotational Newton's second law says MA is equal to the vector rho cross the force vector where rho is equal to P minus A. And what are P and A? We could keep doing this forever. This is where the force is applied. So that's coordinates. And this is the coordinates of the axis. So it's a vector going from the axis to the point where the force is applied. Okay, so let me do an example, and I'm going to do an example where it's not too bad to use both definitions to do it, and we're going to do it both ways. Bless you. So calculate the moment about A using both definitions. And this is the object. It has a length of 1 meter. And this is the axis A. This angle's 30 degrees. And the force is applied at the other end. It's 200 newtons down. So we want to calculate the moment applied by that force about the axis A. So first we're going to use this definition where the absolute value is equal to the force times the distance. Counterclockwise is positive. Clockwise is negative. Anyone remember what that D means? What? It's a distance, and the
Between the forces, line of action.
yes, that's right, exactly. So to use this, you have to be able to imagine the force's line of action. The force continues in both directions. So D is the distance from A to the force's line of action. And how would you calculate that D for this problem? Or somebody go up there and show me what distance we're calculating. Someone.
So wait, what's the NS then to the right of the red dotted line?
Definitions.
Okay, so that's not part of the problem. Okay.
No. Someone march up there and show me what distance we're calculating. And remember to march. Okay.
Left, right, left.
Yeah.
Right.
There to there. Very good. That's the distance we want. The distance, the shortest distance from A to that line of action. Okay? So how are we going to calculate that?
Use either sine or cosine, but I'm pretty sure it's a good 3 over 2. If it's 30 degrees.
Yes, you're right about all that. So, yeah, we're going to do, so if this angle's 30, we're going to multiply the length times the cosine of 30 to get that distance. So D is equal to 1 meter times the cosine of 30 degrees, which is, like you said, square root of 3 over 2, or 0.866. And so the absolute value of the moment is equal to 200 times 0.866. And then we have to think about the sign. So in this case, would that cause, so if you're always thinking of that axis A as what it's rotating around, would this cause a clockwise or counterclockwise rotation around A? Counterclockwise? So this is positive. And so we get 173.2, I think. I think that's right. And the units are what? Newton meters, yeah. Any questions about that? Okay, now let's do it the other way. For this example, the first definition is a little easier to use. That's not always the case. But to use the second definition, so we're going to use that MA is equal to row vector cross force vector. Does anyone know what we're going to get for the moment when we use this definition? The same thing, that's right. Otherwise, one of them doesn't work. Okay, so that row vector, rho is equal to the coordinates of where the force is applied minus the coordinates of the axis. So what are the coordinates where the force is applied? Well, we have to choose a coordinate system, I guess. Might as well choose this one. What are the coordinates where the force is applied?
Negative cosine 30, sine 30.
That's right. So negative 1, and actually you could think of it as, you could think of this angle as 150, and then it's 1 times cosine and sine of 150 degrees. But yeah, that's going to be negative 1 times cosine of 30, positive 1 times sine of 30, and that's negative 0.866, positive 0.5. Whoops. No, that's right. And then what are the coordinates of the axis A? Yep, that's where we put the origin. So the row vector is negative 0.866, positive 0.5, minus 0, 0. So negative 0.866, positive 0.5. And what's the force vector in vector components? That's right. 0, negative 200. And so the moment is equal to the row vector crossed with 0, negative 200. So it's this times this minus this times this, and you get positive 173.2 Newton meters. One thing I want you to notice here, this is an important thing. It's important to us because of moments, but it's an important fact about the cross product in general. The order matters for the cross product. If you have a vector A and you cross it with B, that's the negative of what you get if you take B cross product of A. Okay, thanks. So, so when you calculate this moment, if you're using this second definition, where is that second definition? Here it is. If you calculate that moment as F crossed with the row vector, you get the opposite. Your answer is opposite. Okay, you get the wrong answer. That's sort of a funny thing. It's a little hard to get used to because every other multiplication type operation that we ever use, order doesn't matter. Well, multiplication order doesn't matter. the dot product from calculating work, the order doesn't matter, but cross product's different. Okay? If you don't believe me, believe David. He'll tell you the same thing, right? Thank you. He'll back me up. Okay, so let's do another example. So let's say this is the object. And this is the axis A. Oh, sorry, I wasn't supposed to put this right in the middle. It's supposed to be down here. Okay, so there's the axis A. This distance is 0.2. And this distance is 0.5. And there are three forces acting. A force of 50 newtons acting down at the top. A force of 100 newtons. And then a force of 200 newtons acting at a 30-degree angle. And the question is, what's the net moment about A? Okay, so how do you think you're going to do that one? What's the idea of calculating the net moment? How are you going to do that? Yeah, so you're just going to calculate the moment produced by this one, calculate the moment produced by this one, calculate the moment produced by this one, and then add them up. Okay? Just like net force. Okay? Okay, so one by one we have to calculate the moment produced by each one of these forces. So m net is equal to, so let's think m net about A is equal to m produced by the 50 about A plus m produced by the 100 about A plus m produced by the 200 about A. So, okay, let's think about the 50. There's the force. For this one, I think the easiest way to do it is using definition 1. There's the line of action. What's the closest, the shortest distance between the axis of rotation and the line of action? 0, so D is equal to 0. Anytime the line of action goes through the about point, through the axis, D is equal to 0. And so the moment produced by the 50 about A is equal to 0. Okay, so let's go on to the second one. So there's the axis. There's the 100. Here's the line of action. What's the closest, the shortest distance between the line of action and the axis? In this one, it's 0 also. So D is equal to 0. So the moment produced by the 100 about A is equal to 0. And now the last one. of that force. So is there an easy way to use definition 1 that you can think of? I think in this one it's probably a better way to go to use the second definition. So let's choose a coordinate system. I guess, why not here? What are the coordinates where the force is applied? 0. What are the coordinates of the axis? That distance is 0.2. Yeah, 0, positive 0.2. And so the row vector is 0, 0, minus 0.2, which is 0, negative 0.2. So this is the row vector from A down to here. So if you can just do that in your head, you can skip all this about finding the coordinates. And then the force vector is 200 times cosine of 30 sine of 30 which is positive 173.2, positive 100. And so the moment about A is equal to, okay, so we got 0, negative 0.2, crossed with 173.2, positive 100. This times this, minus this times this, and you get whatever we got for the last one. What did we get? I never did it, did I? Oh, no, what am I talking about? So we got 0 minus negative 0.2 times 173.2. So what's 0.2 times 173.2? 34.64. So we got positive 34.64 Newton meters. And then m net is equal to 0 plus 0 plus 34.64. So you get the same thing. Any questions about that? One thing you should notice here, so notice there's really a third option you could use here for calculating a moment. You can also use the true distance from the force point to the axis and use the part of the force that's perpendicular to that. That's perpendicular to that line. That always works for moments, so if you want to do that instead, you can. So what that means in this case is, what's the distance between where the force is applied and A?
0.2.
Yep, 0.2. And what's the part of the force, of this force that's perpendicular to that line?
200 cos that.
Yeah, it's the x component of that force. And then you have to think about, then you have to use the positive counterclockwise, negative clockwise, clockwise. So in this case, you'd say 0.2 times 173.2, and then you'd have to think, would this force create a clockwise or counterclockwise rotation about that axis? It would be counterclockwise, and so that's positive. You get the same thing. Okay, so finally we're at the rotational version of Newton's second law. And it says this: the net moment about A is equal to the moment of inertia about A times the angular acceleration. And there are two choices for A. A can't be anything. A is either a fixed point, like a hinge, or it's the body's center of mass. Okay, so what are the two choices for the about point? For the axis location?
Center of mass or the fixed point of rotation.
I like you even said the order backwards. You made it your own. I like that.
Paraphrase.
Yeah, I like it. Good job. Okay, two choices. True or false? There are three choices for the axis. False, correct. You're right. Okay, I think you're, at least you and Josh are getting it. I don't know about everyone else, but. Okay, so let's do an example. So say you have this slender rod that's connected to the ground by a hinge, and this angle is 60 degrees. And let's say that at the instant shown, this object has an angular velocity that's equal to 10 radians per second. The question is, oh, and I need to give you some stats about this thing. Let's say this is 1 meter. Ooh, let's do this as two parts. So what's the acceleration of that point P if first the angular velocity at that instant is equal to 0, and second if that angular velocity is equal to positive 10 radians per second? And the weight is acting towards the bottom of the page. Okay, so for any time you're going to use Newton's second law or the rotational Newton's second law, you need to draw a free body diagram. So there's some force down here acting that, I'll just call it R. We don't know what that is. It turns out that's not going to come into our calculation. And then we have a weight force here, mg. Oh, and where does the weight act now? With particles, that didn't matter. But with rigid bodies now it does, because forces can act at different places. So, yep, that's right. So the weight always acts at the object's center of mass. Okay, so let's first calculate we know we're going to use the rotational Newton's second law, so let's first calculate the moment of inertia. So moment of inertia about that axis A is equal to 1/12 times the mass times the length squared. And then you have to use the parallel axis theorem. I talked about that last time, right? So the parallel axis theorem says, so this is the moment of inertia about the center of mass. And now we have to add m times the distance from the center of mass to our axis. What's the distance from the center of mass to our axis? What's the distance from 0.5 meters? The whole thing is 1 meter long, so that distance is 0.5. And so you get m over 3. And now to calculate m net, well, what's the moment produced by the force R about A? We don't know anything about the direction of this force, but we do know no matter what direction it's in, its line of action goes through the pin because it's actually acting at that pin, at that hinge, right? So, I mean, it's like the thing with the bolt. Okay, so you want to turn that bolt. You have this wrench here. How hard do you have to apply a force here to turn that bolt? It doesn't matter how hard you apply it, that it's not turning the bolt. It's just going to rip it off the wall, right? So that's what's happening with this force R that's being applied by the hinge. And now the moment produced by mg, that's equal to, so plus or minus, the force is mg. What's the distance from the line of action of that force to the axis?
0.5 meter.
Well, this distance is 0.5, so I guess it's 0.25, right?
Oh, okay.
But yeah, you just do that trigonometry. That's 60 degrees. This is 0.5. So it's 0.5 times cosine of 60. And then is it a positive or negative? Negative. Yep, that force, if you apply that force is the only thing acting, and this is where it rotates. That force is going to make it spin around this way. And so that's negative. And so the moment produced by the weight is equal to negative 0.25 mg. And so m net is equal to negative 0.25 mg. And so now the moment equation, the rotational Newton's second law, says negative 0.25 mg is equal to m over 3 times alpha. The m's cancel, and you get that alpha is equal to negative 0.75 g.
Alpha is the rotational acceleration?
Yeah, the angular acceleration, that's right.
Acceleration.
Yep. And so now this is true no matter, like notice the velocity, the angular velocity never came into any of this. So this is true no matter what the angular velocity is. But if you remember, like all our problems with circular motion, when you're trying to calculate, what we're really asked for in this problem is the acceleration of that point P. And to find the acceleration of that point P, the angular velocity does matter because of centripetal acceleration. And so now we're going to split it up into, we'll answer part A, and then after that we'll answer part B. Okay, so for part A, here's the circular motion. Right, that point's moving around this axis in a circle. What's the velocity direction? So for part A, there's no angular velocity. No angular velocity. So there's no velocity at all because the velocity is equal to omega times r. So there's no velocity. What's the direction of the tangential acceleration?
Down this way, diagonally down. Yeah.
Yep. And then centripetal acceleration would be this way. We're going to see that that's equal to 0 because it needs to have angular velocity to have centripetal acceleration. Okay, so for the tangential acceleration, that's equal to alpha times r. So 0.75 g, and then what's the radius of the circular motion? 1. And it's pointing in this direction. So 0.75 g in this direction. Anyone have an idea how to put that in vector components? What's the angle that we want for cosine and sine? That's sort of the key to this. Yep.
Would it be negative 0.5 G?
No, this, when we're calculating, we're doing the, okay, so sines, plus minus signs are just directions, okay? And when we do tangential centripetal acceleration and velocity, we're doing the directions just based on what we know about circular motion. So you only want to use the absolute values of those.
Okay.
So really this is, you could think of this as absolute value of alpha times r. Okay, so for the cosine and sine, what's the angle that we need to use there? Yep. Yeah, right. And the way that makes sense for me to do this, I don't know, if you have a way that works better, great. But start at the positive x-axis, go positive 60, and now you're there. And then from here to get to this, I'm too short to show that, but we're at positive 60. Now go minus 90, clockwise 90. And now you're in the direction we want. Plus 60 minus 90 gives you minus 30. So the tangential acceleration vector is equal to 0.75 g times cosine of negative 30 sine of negative 30 and so you get, can someone multiply, what's 0.75 times cosine of negative 30?
I've got 0.6495.
Okay, g. And then this one, that's just negative 0.5, so this is negative 0.375 g. And then the centripetal acceleration is equal to omega squared r this direction, so that's 0 since there's no omega. Yep.
I'm not sure if you know this, but on the AP test, if we just left our answer as 0.75 g times cosine of negative 30 sine negative 30, would that
That's fine, yeah.
lose points? Okay.
No, you wouldn't lose any points. I think really they'd probably prefer that. So yeah, I mean, if you want to do this as, what is this? Square root of 3 over 2 times 3/4. So if you wanted to write that as 3 square root of 3 over 8 times g or whatever, that's fine too. Really, going to decimals is a little bit of a, anytime you can avoid going to decimals, it's probably in your best interest on the AP test, because then you have to deal with significant figures, and you could get docked for significant figures, you know. All right, so the total acceleration of P is equal to AT plus AC, and that's equal to 0.6495 g negative 0.375 g. Any questions about that?
The negative 30 degrees, where did you get that from?
That was the thing that I showed up on the, stood up there and tried to,
Angle estimation. Oh, you just estimated that?
how many times have you heard that standing on a chair with wheels is a super good idea? Okay, so you start there, because that's the positive x-axis. Positive 60.
Right there, Wilson.
Now you're there.
Positive 60, Wilson.
Now you're here.
Yep.
Negative 90. Now you're here. It's where you want to be.
Okay.
So positive 60 minus 90 is negative 30.
Okay.
Okay, so now part B. What changes in part B? Who even remembers what this problem is? That's right. So now the only thing that changes is at this instant, the angular velocity is now positive 10. So now the velocity, there's a velocity vector that doesn't matter for the acceleration. We still have that the tangential velocity, that's the same. That doesn't change. The centripetal acceleration is equal to omega squared r pointing in this direction. Omega is 10. R is 1, so that's 100 pointing in this direction. So what's that in vector components? So let's go back up to this picture. Start at positive, or start at the positive x-axis, positive 60 to get there, then plus or minus 180 to get there, so 240, or negative 120, either of those work. So we have 100 times cosine of 240, sine of 240. And that is, that's negative 50, negative 86.6, I think. And so the total acceleration of P is 0.6495 g, negative 0.375 g, plus negative 50, negative 86.6. And you get something like negative 21.81, negative 45.14. Any questions about that one? Yep.
How do you get negative 21.81 by subtracting 50 from 0.6495?
Because there's a G in there.
So you multiply by 98.
Yep.
Ah,
That's still, that's still wrong, though, isn't it? That doesn't make any sense. I don't know. Let's just leave it here. Then no one can complain. Okay, so here's one for you to work on. So let's say we have a playground carousel. It's rotating around the middle. And we have these things for the kids to hang on to. We'll use a coordinate system like this. And let's say 1,000 Newton force is applied here, and 1,000 Newton force is applied here. The mass of the carousel is 200 kilograms. The angular velocity is 1 radian per second, positive. The radius of the carousel is 2 meters. And the question is, what's the acceleration of this point P? All right, here's a question. Is there any reason to draw a free body diagram for this question?
They look cute.
There is a reason. That's not it, but yes, Meredith is right. You should draw a free body diagram. How do you know when to draw a free body diagram?
If you're using the
Yeah, Newton's second law or the rotational Newton's second law. You always have to draw a free body diagram. So I'm going to do it in a top view, which is what all of you chose to do. That's great. There's some kind of force here. We don't know what it is, but there is some kind of force there. And then there's a 1,000 Newton force here and a 1,000 Newton force here. The moment produced by that force R about A. Sorry, before I go to that, let me do the moment of inertia. So the moment of inertia for a disk is 1/2 times the mass times R squared. And for this one, that's 400 kilogram meters squared. And now we have to calculate the net moment. What's the moment produced by R? 0. The moment produced by the...
So why exactly is it 0? Because it's at the...
Because it's at the axis.
Okay.
Yep. So now let's... okay, so top force. Let's do that one. You can use either definition, but I think here the easiest way is just to figure out the distance from the axis to the point you care about, multiply it by the force. So the force is 1,000. The distance from the axis to the line of action of the force is 2. And then we're doing the top one. Would that cause a clockwise or counterclockwise rotation? Counterclockwise, so that's positive. So we get 2,000 Newton meters. And then the bottom force, the force is 1,000. The distance from the axis to the line of action is 2. Would that cause a positive or negative rotation? positive again. So that's another positive 2,000. And so now the rotational equation says 2,000 plus 2,000 is equal to 400 alpha. And so alpha,
1,000 alpha.
what?
Oh, okay, never mind. So you adding them together.
Okay.
But you're not.
And then, so alpha is equal to positive 10 radians per second squared. Okay, so now we're done with the kinetics, and now we're just on to the kinematics, like the stuff we were doing in rigid body kinematics, and even the stuff we were doing in circular motion a long time ago. So there's the body. There's our point P. The velocity is, the angular velocity is counterclockwise, so the velocity is this way. The angular velocity is in the same direction as the angular acceleration is in the same direction as the angular velocity, so the tangential acceleration is that direction. And the centripetal acceleration is this way. So AT is equal to the angular acceleration times the radius. So that's 20 meters per second squared down. So what's that in components? 0, negative 20. And those units are meters per second squared. And then the centripetal acceleration is the angular velocity squared times the radius. So 2 in this direction. And so what are the components for that? 20 meters per second squared. So the total acceleration is AT plus AC, so 2, negative 20 meters per second squared. Any questions about that? Okay, let's stop there for the day. We'll do 2 more example problems next time, and then we'll move on to possibly the last topic. We'll see how things go, but we're getting towards the end now.